My name is Jashwanti Mandalapu. I am a graduate student from IIT Madras. In this presentation, I am going to discuss about the classical capacity of quantum Jackson network with waiting time dependent erasures. This work is a collaborative effort along with my advisor, Professor Krishna from IIT Madras. I would like to thank all the organizers, TPC members and reviewers of ITW 2022 for providing me with this opportunity. Going forward, what is this talk about? Briefly, this talk is all about the fundamental limits of classical communication using quantum states that decohere as they traverse through a network of queues. We first introduce a quantum queue channel, which is a basic building block of quantum Jackson network. We see the modeling of a quantum queue channel where noise is due to the waiting times of qubits in the queue. We also see the exact capacity for quantum erasure queue channel as a function of waiting time in the queue. Next, as part of this work, we try to extend the capacity of a quantum erasure queue channel to a quantum Jackson network with erasures. Roughly, a quantum Jackson network is a network of Markovian queue channels where erasures occur as qubits traverse across queues in the network. In our work, we consider two types of quantum Jackson networks, namely repeater assisted and repeaterless, and derive the classical capacity from each source to destination node. Further, we also provide optimal pumping rates and optimal routing probabilities in some special cases of quantum Jackson networks. So, without further ado, we first see what a quantum queue channel is. Consider a sequence of classical information bits encoded into qubits. These qubits are sequentially sent over a continuous time single server queue according to a stationary point process of rate lambda. We assume the processing time for each qubit is IID according to some distribution having mean mu. For simplicity, throughout our work, we assume mu to be equal to 1. The waiting time of each qubit j, denoted by Wj, is given as the difference between the departure time of jth qubit and the arrival time of jth qubit to the queue. For an erasure queue channel, the probability of jth qubit getting erased is modeled as an explicit function of its waiting time Wj, which we say P of Wj. In other words, qubit j remains unchanged with probability 1 minus P of Wj and is mapped to a fixed erasure state E with probability P of Wj. The function P here could be any non-decreasing function with waiting time W. Often, in many quantum systems, we consider exponential decoherence where P of W can be modeled as 1 minus e power minus kappa W, which says more the waiting, the more probability of getting erased. The constant kappa here depends on the implementation and some physical parameters such as temperature. It can easily be seen that the quantum erasure queue channel is not a stationary channel because the probability of jth qubit getting erased depends on its waiting time Wj. Further, we know the waiting times in any queue follows Lindley's recursion, which in turn creates memory across the received sequence. Henceforth, we say that the quantum erasure queue channel is a non-stationary channel with memory, where the real challenge comes up. For this quantum erasure queue channel, the single letter capacity expression was characterized in the paper titled The Classical Capacity of Additive Quantum Queue Channels. And the capacity is given as lambda times expectation of 1 minus P of W in bits per second. This capacity expression holds true irrespective of whether or not the decoder knows about the arrival and departure times. the expectation in the capacity is taken over by which is the stationary distribution of waiting times in the queue. Further, it was also proven that the result does not depend on any specific queuing model or any functional form of P. In case of exponential decoherence, we see that the capacity is nothing but lambda times the Laplace transform of waiting time distribution in the queue. With this in hand, we now try to find the fundamental limits of quantum Jackson network with erasures. Using the above Q channel framework as a building block, we construct a network of Q channels to model erasures due to waiting times in the queue. Specifically, we name it as a quantum Jackson network, which is a network of Markovian queues with Bernoulli routing. The question of interest now is, what are the fundamental limits of classical communication over this network of Q channels? This work provides the classical capacities of quantum Jackson network with erasures from each source to destination node. In order to be consistent with the models of quantum systems, we model quantum Jackson networks with two types of queues. One, the repeaterless case where general processing of qubits happen at each Q channel. And two, the repeater assisted case where each Q channel serves as a quantum repeater. As in, the coherence times of qubits are statistically restarted at each Q channel. For simplicity, we do not consider any hybrid networks with both repeater-assisted and repeaterless queues in the network. However, our results can easily be generalized to hybrid networks. Before going to the final results, we first provide the capacities for two simple network topologies, namely tandem and parallel Q channels. A tandem Q channel is a Q channel that has m-1 Q channels connected in series, and a parallel Q channel is a Q channel that has two Qs in parallel with routing probability delta. First, consider a repeaterless tandem Q channel. The capacity here would be nothing but the capacity of a single Q channel, except that the waiting time in capacity expression would be sum of all waiting times in MQ channels. Whereas in a repeater assisted case, the capacity would be little different because the waiting times are statistically restarted in each Q channel. Hence, the capacity expression is given as lambda times expectation of product of all Q of Wi's, where the function Q of Wi is defined as 1 minus P of Wi. Note that all capacity expressions are being stated in bits per second. When the coherence times are exponential, we have a nice closed form expression for the previous capacity result, which is given as here. Note that this capacity expression remains the same irrespective of the network type due to the memoryless property of exponential distribution. Fixing all mu i's to be equal to 1 and m equal to 2, we have the following plot for capacity with respect to lambda. The plot says as lambda is closer to the service rate mu, more congestion happens, leading to more decoherence of qubits, which in turn causes more erasures, reducing the capacity. However, we see that there exists an optimal lambda where the capacity is maximized. But the challenge is that the capacity curve is a non-convex function. Nevertheless, we were successful in finding the optimal lambda for homogeneous tandem Q channel with MQs, and the expression is stated here. Note that we can also find optimal lambda star for heterogeneous tandem Q channel. However, it would be little cumbersome. Next, we characterize the classical capacity for parallel Q channel with the delta as the routing probability. The theorem here states the capacity result. Using this capacity expression, we can also characterize the optimal lambda for given routing probability and optimal routing probability for given lambda to maximize the capacity. The expressions were not stated here in view of the time constraints. Finally, using the results of simple topologies, we characterize the classical capacity of quantum Jackson network from each source to destination node. For exponential decoherence, irrespective of the network type, the capacity expression for Jackson network is presented here, where gamma is defined as the route or a path that is taking us from a source to destination node. More general results for different network types can be referred from our paper. In summary, we have seen the quantum Q channel, which captures errors or erasures in quantum communication. We have seen the capacity expression for quantum erasure Q channel, and using this as a building block, we have come up with network of Markovian Q channels, which we refer to as a quantum Jackson network that is amenable to exact analysis. In specific, we have seen the capacities of simple topologies like tandem and parallel Q channels in both the network settings, namely repeater assisted and repeaterless cases. We have derived optimal pumping rates and optimal routing probabilities in simple topologies. Finally, we extended the results to the classical capacity of quantum Jackson network from each source to destination. In future, we can think about quantum Jackson networks with more noise models apart from erasures. Or we can formulate a multi-objective optimization problem from the derived capacities with an aim to find the Pareto optimal frontier for transmission rates. Finally, I would like to conclude this talk by saying that our work broadly quantifies the importance of explicit modeling of delay-induced errors in quantum communications. Thank you.